Okay. Welcome to the Monday of the second week. Nice to see many new faces. I hope you had a nice trip to Madrid. We will start the week with the Yixin. We'll talk about Xiyin, sorry. A little bit. And we'll talk about renormalized conformal perturbation theory from string field theory. Please take it away.
Thank you. I will attempt the nearly impossible task of convincing bootstrappers that string field theory is useful, specifically for quantum field theory. The talk is mostly going to be based on this recent paper with Ben Mazzo, Joshua Sandor, Charles Wang from March of this year. The title of the paper is somewhat different from the title I gave for this talk. So depending on what audience I give this talk to, usually to a string theory audience, I will phrase this as an effort to understand string backgrounds using string field theory. But to a Bootstrap audience, I'll phrase this as an attempt of understanding renormalized conformal perturbation theory, specifically in 2 dimensions. And I should say that now, if you don't know anything about string field theory, do not worry. I will introduce everything that you need to know about string field theory in the duration of this talk, hopefully. I should say that this kind of connection between renormalized conformal perturbation theory and string field theory is not new. It goes back to actually the early days, the very beginning of closed string field theory, particularly this paper, which is not particularly well known, by Mukherjee and Sen back in '91. The recent work has some, for various reasons, there are various kind of technical progress that allow us to go a little bit further, both in terms of understanding conformal perturbation theory using string field theory and also going the other way around. Let me begin. Okay. All right. Let me begin by just saying briefly what I mean by renormalized conformal perturbation theory. So the naive conformal perturbation theory is what we normally do, that we start with from CFT, and we consider a deformation that's described by, let's say, deforming the quote-unquote action of the CFT by the integral of a marginal or relevant operator. Let me just write dx phi of x. I'm not specifying the space-time dimension here, where this phi is either relevant or marginal. And we are instructed to insert e to the minus delta s into correlators. Usually, this exponentiation of the integral of the deformation operator needs to be defined with a suitable UV regulator, or a regularization scheme, which is distinct from the notion of renormalization scheme, which will be considered in the context of the renormalized version of conformal perturbation theory. Let me contrast this to the renormalized, what I would call the renormalized conformal perturbation theory. And for the convenience of kind of conceptual framework, but also for comparison with the string field theory approach that I'll introduce shortly, I'll refer to this as the Wilsonian renormalized conformal perturbation theory, which is, to my knowledge, not discussed too often. In fact, in this very explicit way in the literature. So, in this approach, instead of inserting e to the minus the integral of the action, which is the integral of this relevant marginal operator over all of space-time, I'm going to insert a Wilsonian regularized version of it. Let me write in this way. I'll just call this bracket regularized. And what this means is that let me not attempt to move it. So this is defined to be sum over n from 0 to infinity, minus 1 to the n over n factorial of integral, as you would normally exponentiate this expression, phi x1 phi xn, But I'm going to restrict my integration domain to some domain. I'll call it Vn, where this Vn, this is a suitable domain defined through a Wilsonian cutoff. So for example, in a point splitting scheme, I would write this as xi minus xj greater than some distance r. Now, I want to contrast this to the previous slide with by emphasizing 2 points, which is that, first of all, this r is supposed to be the floating cutoff in the sense of Wilsonian RG. And this phi should be viewed as not just a relevant or marginal operator, but generally a linear combination of all, let's say, scalar operators in RCFT. Now, this is sort of naturally what would be the analog of the Wilsonian phase action in the language of conformal perturbation theory. Okay, I guess I wrote too big. I have to flip page again. All right. So the notion of the RG transformation, the Wilsonian RG transformation, will be such that let's say this Vn, this domain, was defined with respect to this Wilsonian cutoff distance scale r, and I'd like to change this to Vn of r plus delta r. Let's say go to a slightly lower cutoff momentum scale or distance scale. Then correspondingly, I would like to transform phi to phi plus delta phi, where the delta phi is, so remember this phi was an combination of all scalar operators in our theory, including all the possible irrelevant scalar operators. So this delta phi, and if you expand the phi on some basis of operators, this delta phi is going to involve arbitrary, potentially arbitrary nonlinear combinations of these coefficient TKs. Right, so this, and generally expect this to be built out of the OPEs such that the effect of the deformation, this regulated insertion of the e to the minus delta s, remains invariant. So that's what we mean by Wilsonian RG in the context of conformal perturbation theory. Now, if you actually try to carry this out for point splitting scheme, at the first non-trivial order, you get a delta phi that is just integral of phi phi OPE, or recover the standard result of the sort of the first non-trivial order conformal perturbation theory. But when you proceed to higher order, at least in point splitting scheme, you get into a bit of a mess. In fact, at the moment, I'm trying to sort out this mess and just formulate this directly in this language. But in this talk, I will discuss a streamlined approach that's already kind of in place, which is applicable to two-dimensional conformal field theories in the language of string field theory. But at the heuristic level, it's a particular way, or you can think of it as a particular scheme to formulate this kind of Wilsonian renormalized conformal perturbation theory in 2 dimensions. And for any CFT. Now you may, when I say string field theory, you might think, oh, you have to think about the worldsheet of a string, has critical center charge and so on and so forth. That would be the case. However, we'll see that we can, in fact, embed the arbitrary 2D CFT into this framework. But in fact, even before going to that, I would like to motivate this further by just describing a specific example. It's not the simplest example of this sort, but it's an example that kind of illustrates some non-trivial features of this renormalized conformal perturbation theory that's also relevant for some addressing some questions in string theory. So let me discuss a 2D example. If I'll discuss 2 examples in this talk, this will be the first example. Let's consider a CFT, let's call it M, which would be some compact CFT. Let's say we can assume this to be compact. Well, there are too many CPTs, so we'll not call this compact. tensored with n free bosons, n free non-compact bosons, which are called, denote the fields by xi, I runs from 1 to n. So suppose this compact CFT M has a pair of marginal primaries. I'll call them phi 1 and phi 2, such that the OPE have the following selection rules. Phi 1 contains identity and phi 2 plus irrelevant operators. Phi 1 times phi 2 contains phi 1 plus irrelevant operators. And phi 2, OP with phi 2, contains identity plus irrelevant operator. Okay, so this is nothing unusual. A prototype, let's say prototype example would be, let's say M itself could be a compact free boson and with some suitable radius, and phi 1 is cosine of square root 2x. Here I'm using a specific normalization convention for the free boson, so-called alpha prime equal to 2 convention, such that this cosine of square root 2x is marginal, and phi 2 would be partial x, partial bar x. Okay, so that'll be an example of this kind. Now, right. I should have written smaller. Anyway, so specifically, we're going to consider the following deformation. Delta S, the variation of action, is integral over our space. I'll write the measure as d squared z. Phi 1, something combination of phi 1 and phi 2. Now, this phi 1 and phi 2 are marginal, but if you turn on both of them, they're not exactly marginal because of non-trivial 3-point structure constant, phi 1, phi 2, as I assumed earlier. But you could try the following. You could consider some sort of more complicated deformation that involve these other, remember you have these other n free bosons that come along with the right. F of x phi 1, g of x phi 2. Okay, and you can ask, is there a new fixed point? Now, in the naive, let's say, if you approach this from the naive conformal perturbation theory perspective, you might want to start by taking f and g to be such that this deformation is marginal to first order and consider correction on top of that. If you do that, so the first order, if this would be marginal, you would say that you would require f and g to be harmonic functions. That would do the job. If you, for example, demand this function f and g to fall off at infinity, then there are no such harmonic function. I should say, maybe I should say here, the new fixed point. Well, okay, let me just leave it as that. In fact, you might expect that if the f and g, let's say, fall off at infinity, then there are no such harmonic functions because they have to be singular at the origin. Just because these functions f and g diverge somewhere in the target field space doesn't mean this deformation doesn't define well-defined quantum field theory. In fact, it's precisely because these are naively, in the naive conformal perturbation theory, you think of this f and g as Taylor conventions are Berry couplings, and they could well diverge, whereas the appropriately defined renormalized coupling will remain finite. So in fact, in the appropriate renormalized conformal perturbation theory, Well, you want this to be of weight, because these are already, phi1 is already marginal, so you want the f of x to be of weight 0. It's just a function of free boson, and the weight 0 means that it has to be a harmonic function. Fx being weight 0. Right. So in renormalized conformal perturbation theory, whoops, a bit of a challenge to. Okay. In renormalized conformal perturbation theory, I'm not going to specify for now the precise scheme, but in a suitable scheme, you will find that at least to the first non-trivial order, the condition for the fixed point is in fact given by the following equations. This second order term come from the phi OPE. And in fact, this have non-trivial solution for a suitable number of the free boson X. In fact, we do believe that there are new fixed points described by solutions. In fact, a kind of a family of solutions to these differential equations. These in the string theory literature are known as the Horowitz-Polchinski string star background. Anyway, so here I'm just giving one example of sort of this, the use of this renormalized conformal perturbation theory in describing some fixed points that's sort of hard to, would be perhaps a bit hard to understand if you don't work with the renormalized deformation parameters. Yeah. It depends on. I'm not sure what you mean by naive. You can do this. You can arrive this equation in the same sort of way as how Zemologikov originally computed. Things like central charge shift and operator spectrum to second order. But that is renormalized conformal perturbation theory. That is so. In particular, the coupling, which are this f and g function here, the coupling that are involved in this equation are already the renormalized coupling. Sorry. The X fields do come in. The number of the X fields, well, they only come in to the extent of what kind of solution this differential equation have, and that's something you can just analyze by looking at these differential equations. I think the kind of solution where f and g asymptote to some finite constant infinity are such that I think this n has to be like between 3 and 5 or something. All right. They can be made arbitrarily small. So they're asymptotically they approach some constant, but the constant can be made small. So there's a consistent approximation in which this equation is valid. Anyway, this is not the main example of this talk, so I'm kind of skipping some details here. Yeah. Naively, it would look like.
Still don't, okay. If you take f and g constants, do you have a fixed point even naively? Because the phi1 and phi2, they have like the OP coefficient of phi1 plus phi2 with itself is non-zero from what you told us, no?
These are supposed to be the correct equation that describes.
I agree with that. I don't understand why naively I should expect this to be marginal if I take, in the simplest case of f and g being constants,
first order, marginal at first order. I'm just saying the operator is marginal by assumption. The phi1, phi2 are marginal by my assumption.
Oh, so the classical term, not the one loop term.
So a pair of marginal primaries, that was my assumption.
Oh, yeah, okay.
All right, so that's why I consider this specific example. So maybe just one more word about this. In the original Horowitz-Polchinski star solution, this is supposed to describe the worldsheet CFT of a string background where this compact boson is the T-dual of the Euclidean time circle, and this cosine is T-dual to a 1D mode that, anyway, that's the connection to the string star story. All right. Okay, so now let me discuss the string field theory. So we're going to embed 2D CFT first into the worldsheet. This is just for the setup of this specific of this talk. This is by no means a universal thing, but this is going to be a setup I'll discuss the connection to string field theory. So let's say A, this both phase A, is a CFT of interest. So this is any theory you want, pos model, couple pos model, whatever. Okay, so it will have some central charge, which I'll denote by CA. And as you probably know, at least in the bosonic string, you want the worldsheet theory to have central charge 26 for the matter sector. So this, I'm going to add to this. I guess I'm not very consistent with the direct sum versus tensor product notation. I guess I'm using direct sum here to denote product theories, where this M is some auxiliary CFT. I'll call this a mock CFT. It doesn't have to be an actual CFT in the sense of you know, closed OP and modular invariance and all that. I will say what property it needs to have, but it, at the minimal level, it needs to have a Virasoro algebra, and we'll assume that has a vacuum module. Where central charge is 26 minus CA. And then we have the usual, what's known as the BC ghost system. So this is familiar to string theorists, but I'm not going to assume that you're all familiar with this system, so I'll say a few words about this. It has a charge minus 26. So this is going to be a setup. Let me just say again that A is a CFT of interest. M, I don't really care what it is, except that it has this Virasoro algebra and suitable modules with back to the Virasoro algebra of this inner charge. And the BC ghost is a free non-unitary theory of the following properties. Oops. Right. So the BC ghost system. Let me actually make a comment. So this is. It will seem kind of ad hoc at this point. You might think that I'm introducing some extra gadgets that bear no actual role in terms of analyzing the CFT A itself. It will, you know, I think I don't have the full understanding of this, but superficially it will be seen that this ghost system is actually useful to understand specific class of deformation of 2D theory having to do with the dilaton. It will actually play an important role. But for now, let me just introduce what this thing is. It has the following primary fields with back to this C equals minus 26 Virasoro algebra, which I'll denote by B of Z, C of Z, where these lower indices indicate the rank of the tensor. So this B, for example, transforms in the same way as the stress energy tensor TZZ with respect to the global conformal symmetry. And this C transforms as a vector with a weight -1 because it's upper Z index. And then there are these anti-holomorphic fields, B, Z bar, Z bar, Z. Sorry, B tilde, Z bar, Z bar as function of Z bar, and C tilde upper z bar as function of z bar. So as the notation would suggest, these are supposed to be primaries of weight 2, 0. This is weight 1 minus 1, 0. This is weight 0, 2, and 0, minus 1. These are the weights. There's OPE, non-trivial. Well, the singular part of OPE is between, it's maybe hard to read, sorry, between BZ and C0, goes like 1 over Z plus regular terms. And all the other independent OPEs are regular. And let me maybe just say that the stress energy tensor of the Go system is built out of the B and C in this way. Just to be a bit explicit, and you can verify that this stress energy tensor assigns the appropriate weight to B and C and has central charge minus 26. Now, there are a couple important properties, basic properties of BC ghost system that I should state, which will be very useful. First of all, there's a ghost number symmetry, sort of a U1 symmetry, that assigns +1 to the C ghost and -1 to the B ghost field. This symmetry is, in an obvious way, respected by the OPE. The second is that there's a ghost number anomaly such that if you consider correlation function on the plane or the sphere, the total ghost number has to, well, let's say, let me by convention talk about the total ghost number. An example of a non-zero correlator on the plane or the sphere would involve 3 C's and 3 C tildes. This is equals to Z12, Z13, Z23, the whole thing squared. This means the product of this 6, so C and C tilde. So the total number of the C's minus the number of B's have to be equal to 6. That's an anomaly of this U1 ghost number. So these are some basic properties that we need to know in order to discuss the space of operators of the system. Okay. Now, there are, so that's this worksheet theory. So we have the CFT-A, we have this auxiliary sector, we have the BC ghost. Total center charge equal to 0. The special feature of the total center charge being equal to 0 is that when these conditions are satisfied, there's a BRT symmetry, such that there's a nilpotent BRT operator QB, which is written as the integral of a BRT current, a holomorphic current, plus the anti-holomorphic counterpart, where this JB, the BRT current, is C ghost times the matter stress energy tensor. So by this Tm, I mean the T matter. By matter, I mean, A plus M. So this is what I call the matter part of this worksheet CFT. Right? So C times T matter plus some pure ghost stuff, BC partial C plus 3/2 partial square C. This partial square C term does not contribute to this charge, but it's such that it makes JB a primary with back to the Virasoro algebra. So this is some kind of 1, 0 Virasoro primary. And it has some key properties. So the key properties are, there are two key properties. One is that QB is nilpotent. And the second is that QB acting on the B ghost gives you the full stress energy tensor, which is the matter plus the ghost stress energy tensor. So in that sense, the full stress energy tensor is BRT trivial, and that allows this theory to be viewed as some kind of theory of two-dimensional gravity in the appropriate sense. Okay, so that's some machinery, but I need to talk about the actual string field. So what is a string field? The space of string field is defined as following. This is what we usually call the closed string field. H hat, this is space of string field, is the following linear space, spans by psi, which is a vector living in the matter Hilbert space, tensored with the space states of the BC ghost system. BC ghost state system is not unitary, so this H ghost is not quite the Hilbert space, but we'll not worry about such mathematical subtlety for now. I just view this as a vector space. Subject to some additional constraints. So this could be any, described by any vertex operator, let's say by the state operator mapping, any vertex operator made out of the matter CFT and the ghosts. But it's subject to the following constraint, which are a bit technical, and I'm not going to explain the reason for this constraint except by stating what they are. So this B0 plus minus notation is B0 plus minus B0 tilde, where the B0 is the zeroth mode in the Laurent series of the B ghost. So let's say in the usual notation, you write this BZ in the radial quantization. You write BZ as some n from minus infinity to infinity Bn over z to the n plus 2, where Bn is viewed as the operator acting on the vertex operator inserted at the origin in the usual way, and this L0 plus minus is the analogous combination of the Virasoro generators, L0 and L0 tilde. So this condition, the second condition, simply means that psi as the operator has zero spin. All right, so this is just a definition. All right. So for example, the psi, some admissible example of string field would be you can take C tilde O1 matter plus partial C tilde O2 matter plus da da da. You can take arbitrary combination of the ghost and the matter vertex operator, where this O are some kind of some suitable operator in the matter sector, with no constraint on the weight except that the total spin of this has to be 0. Actually, I think I wrote this already slightly wrong because this is not going to obey that condition. So let me write something. Anyway, let me not even bother to write this term here. So here's an example of a admissible string field. Let me just emphasize here that this CC tilde, this is in fact the lowest weight state. Lowest weight state in the ghost space of states. It has weight -1, -1. All right, so all the other states are either have the same weight or have higher weights. One of the lowest weight states. Okay. Now, I need to tell you the dynamical contents of the string field. So I already so far introduced the space of string fields, which is just this. Okay. Now, the content of the string field theory. Here, I'm going to discuss just the classical version of the string field. It will suffice for my purpose. classical bosonic and closed string field theory. It's characterized by the following equation of motion. So we have the string field, but just like any kind of classical field theory, there's some configuration space for the fields, and then there's the equation of motion that governs what are the physical, the admissible field configurations. The equation of motion is the following. So QB psi plus some nonlinear interaction terms are written, that are written in the following way, equals 0. So this QB psi is just the BRC charge acting on the string field psi, the charge I have defined earlier. This notation here, this bracket is a map from n, the space of n string fields, so h hat tensor n times, to h hat itself. I refer to this as the n string or n string field bracket. It's a symmetric and n linear map. It has the following properties. Let's see, which one do I want to state first? You can think of this n-string bracket as a sort of product operation, but it's different. It's going to be different from the OPE. So it kind of resembles OPE, or it resembles an integrated version of OPE, but it's not quite the same. It's commutative by definition, but it's not going to be associative. And so now you might think that the algebra defined by some product is not associative will have no structure at all, and that will not be quite the case. There will be some constraint on the algebra involving this string brackets, which I will state momentarily. Before saying that, let me just say that this bracket is supposed to change the Gauss number by minus 2n plus 3, and you can verify that this will be such that so that if psi has a Gauss number equal to 2, as in this previous example of this string field, if psi has Gauss number 2, then every term in this equation will have Gauss number 3. So all the terms have the same Gauss number, and this equation would be non-trivial. So the equation motion has Gauss number equal to 3. Okay, so the key property of this bracket is that it gives rise to what's known as the L-infinity algebra. This word sounds scary. What it means is something very simple. It just means that if you act on this n-string bracket with QB is some kind of differential. It's nilpotent, as I said. It obeys some kind of distribution rule, as an ordinary associative product would, but with some correction. So normally, if you have a differential graded algebra, you would expect some kind of distribution rule of the differential operator like this. But now there's a correction term, which involves nested string brackets. And that's it. Okay, so this defines this so-called L-infinity structure. I want to emphasize that this is really something ubiquitous, and it's something very general that shows up in the BV formalism of gauge theories. Okay, so I think since I'm pretty sure that I'm running short in time, so I should get to the point. I want to say the minimal things I need to say about the properties of this this bracket that will need to be used. So now, for the purpose, okay. In fact, let me. I forgot to say the conceptually most crucial point, which is that okay, why am I talking about the string field theory at all? And the key logical recipe is what's known as the background independence in string field theory. Is this the idea heuristically is the following? So if you consider this worldsheet CFT with some matter CFT and some ghost, this can be viewed as a classical background of bosonic string theory. If you deform the CFT in some way, let's say if you deform the CFT marginally, just for example, in a way that in such a way that preserves central charge, it would correspond to a new string background. Now, this new string background, you can either view that as defined by a new CFT, or you can somehow equivalently view that as defined in the string field theory of defined by the same old CFT, but you turn on a non-trivial solution to the string field equation. Okay, so this is the most essential point. So let me say this again in a slightly different notation. So let's start with some worldsheet CFT defined by this CFT A. You can deform the theory to some new CFT. Let me call it A lambda, where lambda, you can think of this as deformation parameter, maybe the expansion parameter of your conformal perturbation theory. There's an equivalent way to describe this deformation by starting from within the framework of the string field theory, but defined entirely within the A itself. So in the string field theory framework, we'll never deform the worldsheet CFT. So the CFT is never deformed. It's always the same CFT. Okay, so if you know the conformal data of your old undeformed original CFT, the string field theory is fully defined. And we can work entirely within that string field theory, but that string field theory somehow knows about all the deformations of the underlying CFT. So in that string field theory, the old background will be represented by the trivial string field psi equals 0. Whereas the new background is going to be represented by a non-trivial solution to the string field equation, which I denote by psi lambda. And I'll discuss how such a solution might be constructed. So the psi lambda is a non-trivial solution to the string field theory equation. The statement of background independence is that under suitable assumptions, which are not fully elaborated for now, but maybe I'll discuss if there are questions later, under suitable assumptions, there's going to be a one-to-one correspondence between deformations of the CFT and non-trivial solution to string field equation. Now, the dictionary going between this psi lambda and A lambda is very non-trivial, and in fact, I won't have time to fully spell it out. But I will just claim that, in fact, you can extract all the CFT data of A lambda by the appropriate physical observables involving psi lambda and its fluctuation in the string field theory. So, for example, if you want to know the spectrum of the CFT, you just need to study the spectrum of infinitesimal fluctuations around the background string field, just by looking at linearized perturbations around this nonlinear equation of motion, modulo gauge invariance, which I haven't defined, but there's a suitable notion of gauge invariance in the string field theory. And if you want to determine the structure constants of three primary operators in this deformed CFT, you can just look at specific scattering amplitudes, on-shell scattering amplitude in the string field theory around this new background. And there's a specific prescription for that, which is formulated in our paper, and you can reproduce the CFT structure constants. Now, I think, as far as I know, in the literature, there has not yet been a full proof showing that given every non-trivial solution to the string field equation, even constructed perturbatively, you can extract consistent CFT solutions that solve the crossing equation, all that, but I believe that that's a true statement. It's just waiting to be proven. Good. At least within the context of classical bosonic string field theory, the belief is that there aren't any. So any kind of deformation that will mix them two would have to be kind of gauge trivial somehow. And that's part of the content of this background independent statement. I should qualify this by saying that although earlier I was specializing to this situation where the CFT kind of factorized in this form, of course in the string field theory, it doesn't have to maintain this kind of factorized structure, but if you want to apply this to study a deformation where the CFT-A, where center charge changes, which we're often interested in, you just need to consider deformation that also deforms this M, so that to maintain total center charge 26. So this framework is flexible enough to describe any deformation of the CFT-A, essentially. Well, that's the easiest case to analyze. Let's say if you have a deformation of A that's exactly marginal. Oh, yeah. So that's what the comment earlier was for. Let's say if A is a convex CFT with a slightly relevant deformation that follows a new fixed point, whose new center charge is slightly smaller. In that case, indeed, if you just replace A by that new CFT, this will not be a consistent string background. If you go ahead and try to look for the corresponding solution in the string field theory, you'll find an obstruction. If I had more time, I would show explicitly how the obstruction arises, but maybe I won't have time to quite do that, show you that calculation, but you'll find an obstruction. Now, you can consider a string field solution that also sort of secretly deforms this auxiliary sector. For example, you can add some linear dilaton CFT and deform the background charge of that linear dilaton to compensate for the center charge. So it is possible to describe a relevant RG flow of the CFT-A within this framework. In fact, this was already considered in the 91 paper of Mukherjee and Sen, and this first order, actually, it's the third order shift in center charge, which is the first non-trivial shift in center charge in conformal perturbation theory, as was originally derived by Zamolodchikov, was indeed recovered by the string field theory calculation of Mukherjee and Sen. That was also kind of reproduced in a slightly different language in a section of our paper.
So I was saying that I'm just slightly confused because when you were introducing the string field theory, you were always referring to A as a CFT, but if you have a slight marginal deformations, there are G flow and there is a scale. So how does this, how does this work out in this story?
Very good. You see, the string field, first of all, the string field is off shell, it's all by default, right? This O1, so this is kind of in fact, this example is kind of a prototype of the kind of string field you would write down if you try to construct a perturbative solution. This will be the first order term you will write down. And if O is a marginal matter CFT primary, then this will be BRT closed, and that will be unshelled to the first order. But it doesn't have to be. Now, you can indeed, if that's the case, of course, to solve the equation of motion, which is on the next page, in order to solve this equation of motion, you have to balance the first order term against some higher order terms. But that's precisely how it works out also in renormalized conformal perturbation theory. So now, there's some data I haven't told you, which is hidden in this string bracket. I think maybe I'll spend my remaining time discussing that. There's some data I haven't introduced to you, and that involves some scale. Because as I was alluding to, this string bracket is some kind of integrated OPE. There's some scale hidden in there. And in fact, the psi is supposed to be viewed as analog of the Bosonian effective action, kind of repackaged in some way, because it's going to contain all relevant and irrelevant matter operators. And in fact, I would say that this string field equation itself should be viewed as an analog of the Wilsonian RG fixed point equation. That is, to set this to 0 somehow finds for you the RG fixed point. Okay. Let me see. I think I need to at least provide some. I should say what are the recipes that goes into define the string bracket, which is the sort of most non-trivial dynamical data in the string field equation, and discuss kind of one non-trivial example of a solution that illustrates the use of this. So this n-string bracket can be abstractly defined in the following way. There's some factors of 2 pi I with a minus sign, which is, I think is unimportant, but actually is quite important. And there's some integral over some domain. So this notation I will define shortly. E to the b product I. Sorry. Okay, so I'm just going to sketch what these things are. So this b0 minus is an operator I've defined earlier already. This is just b0 minus b0 tilde. This p minus is the projection onto onto 0 spin states. As was mentioned before, the string field must have spin 0. So somehow here everything has spin 0. This b, capital B, is something that involves the B ghost. Some kind of integral, some kind of contour integral involves the B ghost. I'm not going to write this in detail. It's a standard kind of recipe in defining string amplitudes. And this Fi is a suitable conformal transformation that goes into the definition of the string bracket, which I will also won't have the time to elaborate. The psi superscript Fi just means the conformally transformed version of the string field psi, which itself is a vertex operator. So you have some product of n of the string fields with some insertion of the B ghost. They come in the form of some differential form. And then you're supposed to integrate that differential form over this gamma n plus 1, which is a domain inside the n plus 1 punctured sphere. It's some suitable domain. And the choice of this domain essentially defines an analog of the Wilsonian RG scheme. Now, I won't have the time to elaborate on what are the precise consistent conditions on the choice of domains together with this conformal transformation, but I will just say that they are subject to a set of constraints which are precisely these constraints so that this brackets obey the L-infinity algebra. So there's some kind of matching condition between the domains of different values of n that have to that will make this work. Now, in the simplest case, if n is equal to 2 for the 2 string brackets, this is more or less like the OPE. So you can have a psi inserted at one place, psi inserted in another place, and you look at the product operator, and you do this B0 minus and this L0 minus projection. In fact, it doesn't have to be this way. Already at this level, there's some choice involved, and if you just do the ordinary OPE at some fixed location, so call it minus Z0 and Z0, this is what we call the flat vertex frame. So there are infinitely many different choices of the string brackets that are compatible. A given choice corresponds to a particular frame for the string field. What that means is that if you work in one frame, you have one set of equation motion. You work in a different frame, you have a different equation motion. But the two are related up to field redefinition. And this is a precise realization of the idea that different RG schemes are related by redefinition of the Bosonian effective action. So I think that's all I'm going to say about the string bracket. You can go on and talk about the 3-point bracket and so on and so forth. There's a well-defined recipe that tells you how that can be constructed, but it will take some time to explain, and I want to just get to the actual more concrete example. So let me illustrate this with an example. I discussed earlier an example of the Horowitz-Polchinski string star. Let me discuss another example, which is a bit more curious. So consider the free boson. I'll take this A to be free boson X. And I'm going to consider the deformation. Consider the deformation just by cosine square root 2 x. All right. So again, my convention of normalization of x is that this is marginal. Now, I'm going to emphasize that this is a free non-compact boson, non-compact free boson. And generally, I'm not going to demand my deformation to preserve any kind of shift symmetry. There's no shift symmetry involved. Okay. So I'm going to consider this deformation. Now, this deformation is, of course, marginal to first order. And I can ask, is it exactly marginal? Now, I think some of you would immediately say no. For example, if X were a compact boson, and you consider this deformation, the answer is no. There's various ways to understand that. There would be a non-trivial beta function, a second order, and so forth. But for the non-compact theory, there's sort of enough room to adjust. There's so many operators you can tune that you can actually always make this marginal. For example, at the second order in conformal perturbation theory, if you found a beta function, you can always cancel that beta function by considering a lambda square order deformation. So the claim is that actually there exists such a marginal deformation to all orders in lambda perturbatively. I want to emphasize perturbatively. Perturbatively to all orders in lambda. In the string field theory framework, one can construct a solution psi, which is some lambda n, psi n from 1 to infinity, that solves the equation of motion order by order in lambda. Now, the details of the solution is quite interesting, and it will take but it will take some time to analyze the details. So I'm not going to, due to lack of time, I won't write the actual details of the solution. I'll just say the most essential features of the solution. So psi 1 is just this CC tilde. So remember this. So psi n are the nth order string field. So to first order is just this deformation, CC tilde times this deformation. To solve psi 2, which is sort of q psi 2 equals something, so by solving the string field equation order by order, you will encounter a obstruction which indicates that the central charge of the CFT A would have been shifted by some quantity of order lambda squared. So in order to proceed, we'll remove this obstruction by also, let's say by including a linear dilaton sector in this auxiliary Mach CFT, and also turn on some some suitable compensating string field, which I will not describe in detail. But anyway, the point is that once you do that, you can remove this abstraction and consider the solution to higher orders. I'm just going to describe, physically what this. Well, okay. Let me just write the. I think I should at least write the form of the string field solution, just to illustrate what this framework can really do. In the end, one finds a solution of the following form. Sorry. Actually, I think at this point it's not very useful for me to write the formula. Let me just describe what solution is physically. So here's X. I'm going to write this in this described solution in the language of the target space of string theory, but all of this can be phrased purely in the language of a 2D CFT. So this deformation cosine, actually let me use so this deformation cosine squared to X. This deformation itself can be viewed as, in the string theory language, corresponding to turning on a tachyon profile in the space-time, which is like so. If you solve the string field equation beyond the linearized order, you'll find that not only the tachyon field needs to be turned on, but there's also one needs to turn on a dilaton. Use the red dilaton profile phi of X. So the dilaton, well, in the string theory language, some massive scalar field in the target space, but in the CFT language, let's say if you think about nonlinear sigma model language, it corresponds to turning on a term in the action that is roughly phi X times the Ricci curvature of your worldsheet. So this dilaton is kind of a weird thing to try to describe in the conformal perturbation theory language. You cannot really write down some ordinary operator if the worldsheet is flat, but it represents some deformation of the stress energy tensor that would make a otherwise non-conformal theory conformal. This is something that can occur in non-compact CFTs in 2 dimension. The string field theory knows about the dilaton. There's a specific component in the string field in a specific gauge that represents the dilaton. I won't have time to explain exactly which term that is, but it involves the ghost in a non-trivial way. All right? So if you solve the string field equation, you'll find that you are also forced to turn on the dilaton profile. So you have this phi of X, and you have this tachyon T of X. So once again, the tachyon profile corresponds to deformation by some function of X. The dilaton corresponds to something like this. And if you solve the equation to higher orders, you find that there's some non-trivial profile such that they diverge at some finite distance, at some finite distance where this distance is of order 1 over lambda. Remember, lambda was the deformation parameter. Lambda was the thing that sits in front of this cosine squared to X. So the thing is this plus higher order corrections. But somehow the profile, you can solve, so the profile such that it becomes singular there, and also the dilaton sort of diverges there logarithmically. Okay, so what is the interpretation of this? This is supposed to describe some kind of marginal deformation of the free non-compact boson by this cosine of X, cosine squared 2 of X. And I claim that this deformation is exactly marginal to every order in lambda. So what CFT do we end up with that somehow correspond to this target space? The claim is the following. The claim is that if you zoom in near the either end of the target space, in the limit, when you send lambda to 0, where these are pushed very, very far, you're still supposed to get the CFT of center charge exactly equal to 1. So here you have some kind of wall. In the limit lambda goes to 0, the center charge is still, of this CFT A, lambda is still supposed to go to 1. So it's some kind of weird C equals 1 theory. In fact, we identified this with something that's already proposed in the literature. The claim is that this is the so-called Runkel-Watts theory. The Runkel-Watts theory was originally defined by Runkel-Watts as a limit of the AK minimal model in the limit k goes to infinity. And they just inspect the spectrum and structure constants and discover that there is a well-defined limit where they have a unitary irrational CFT center charge equal to 1 that solves the crossing equation, but has a continuous spectrum. We showed in the appendix of our paper that if you take the structure constants of Runkel-Watts theory and do some appropriate sign redefinition and the Fourier transform, you will recognize that exactly matches the feature of having a wall in space, in the target space, and have the data time blowing up logarithmically. Okay, so that's a non-trivial observation that's consistent with this interpretation.
I missed a crucial point. You have a parameter lambda here.
Yes.
The Runkel-Watts theory is a single theory.
That's right.
I did not understand lambda.
What I'm saying is that in the limit when lambda goes to 0, these two walls are infinitely far apart. It is in that limit you can isolate this wall by itself. And that's what we identified as the Runkel-Watts theory.
Okay.
Now, when the lambda is not 0, the two walls are fine distance away from each other, and they talk to each other in some way. The claim is that the whole thing is the minimal model, is the AK minimal model, where k is roughly some number over lambda. All right. In fact, this is confirmed by several things. First of all, you can calculate the center charge shift. I didn't explain the detailed ways how the center charge shift is calculated, but I said earlier that you have to include a deformation of linear Dayton sector to compensate for center charge shift. Otherwise, there will be an obstruction to string field solution. So from that, I can deduce, at least to a second order in lambda, how much is the shift in center charge that the deformation of CFT would have had if you use the CFT deformation language to describe this deformation. But much more importantly, you can study linearized fluctuations around the string field solution. And this is somewhat lengthy analysis that will take a whole other talk to explain, which I obviously won't have time to explain here. But you can look at the fluctuation string field around this background. This requires extending this auxiliary CFT sector to include some additional module with reversal algebra, but this can all be performed consistently. And from that linearized fluctuation of the string field, you can extract the spectrum of the CFT or the deformed CFT A. And the upshot is that there are going to be these sort of standing wave type fluctuation of the tachyon field that on top of this background, I don't know what I call it, so some linearized fluctuation, fluctuation that can be identified. So this linearized fluctuation corresponds to some kind of standing wave of the tachyon subject to some boundary condition. This boundary condition we cannot deduce from first principle in string field theory because the string field is singular on the boundary. But by matching with the Runkel-Watts theory, we can guess some appropriate boundary condition. And once we have settled down on the boundary condition, we can compare the linearized fluctuation. We'll find a sort of quantized set of linearized fluctuations corresponding to standing waves subject to some kind of Dirichlet type boundary condition, which are precisely in correspondence up to order 1 over k squared, up to order 1 over k squared, to the spectrum of primaries of AK minimal model at large values of k. So that supports this interpretation. So the upshot is that we come up with this rather surprising conclusion that this deformation, which is marginal to order in lambda, actually give rise to the AK-mu model. Now, of course, for the AK-mu model, the K is discrete, but that's some kind of, that is not in contradiction with this all-order marginality. So it's perturbative to all-order, marginal to all-order. I think that there are a lot of potential generalizations and follow up on this, but I'm already way over time, so I'll just stop here. Thank you.
Sorry, let me answer if I got it. So you're flowing to the AK minimum mole times a linear dilaton to absorb the central charge or something like it?
That's right. So in fact, I should say that the full worksheet theory, I mean, I didn't want to spend too much time on this, on these technicalities, but really what we start with is A together with direct sum linear dilaton together with a auxiliary or mock CFT. So, oh, sorry. We have the A with linear dilaton and also additional mock CFT sector. This beta is the background charge of the linear dilaton, which can be anything you want. And the deformation is such that you will turn on the string field that involve both the A, primaries in A, as well as primaries in the linear dilaton, and we're always working the vacuum module of the mock CFT. Now, generally, of course, you could consider deformations that couple the two, but here we have to work with a string field that maintains that decoupling. It turns out to the order that we have calculated, this decoupling is kind of trivial, but generally going to higher order, which we have not done, you do have to worry about sort of unmixing the two sectors, and there's a decoupling criteria which we propose that you have to check, but that can be phrased entirely of the string field. Yeah. It's true that in the CFT language, the thing we ended up with is supposed to be the deformed A theory and deformed dilaton and the same mock CFT. I'm just saying that in the string field theory language, once again, we'll always commit to the same old CFT. We would never deform the CFT any way whatsoever. But yes, the equivalent, by this background independence, the equivalent you can describe the new background as the CFT.
More questions?
So is your expectation that some discrete values of lambda will become important due to non-perturbative effects and like unitarity will get restored somehow?
Yes. I should say that in some sense maybe it's not really non-perturbative effects because we know the observables are all analytic functions of 1 over k, and all the expansions for physical observables are supposed to converge. Indeed, I think a part of the issue is that our current understanding of closure field theory is entirely perturbative, and we don't really know what to do when the field blows up. I think this and other examples suggest that there should be kind of a kind of more. There's an understanding that's yet to be completed in order to understand exactly what happens to a string field at these places where the string field blows up, and there should be some kind of condition that determines the actual quantization condition on lambda. Let me give you a similar example that kind of illustrates how this should work, which maybe it's kind of more intuitive. So I can also consider another example, which is the deformation from R3 to S3. This will be with H flux. All right, so if you have 3 free bosons, I can consider a deformation, a family deformation that turns into the W0 model SU2W model, which is described as a nonlinear state model as a S3 with some H flux. In the limit of large radius or large level, so there's the radius goes like square root of the level, and here I want to consider the 1 over radius expansion. So from the point of view of 1 over radius expansion, you would like to describe this W0 model as a perturbative expansion starting from R3. So indeed, one can construct such a string field solution. And in this case, you know that this R is R squared is supposed to be quantized. But the mechanism of this quantization has to do with sort of closing the sphere. And if you can just recognize that somehow the sphere has to close, then you understand that it has to be quantized. And I think these are more or less the same issue. And at least in this example, by exploring how the diffeomorphism acts on the string field, one can in principle understand how to complete this S3. But I mean, in the string field theory, if you're working a given gauge, it's similar to like doing GR, but trying to describe this S3, but in a specific coordinate system. And you'll find that the solution is kind of singular somewhere. But if you can move to a different gauge, then in this case, you can recognize that it's actually smooth everywhere, and the space closes up. That somehow is the mechanism that quantizes this K here.
You talked about some operator being marginal to all orders in lambda. I guess this corresponds to some kind of conformal manifold. Can you extend this to several couplings, have a multi-dimensional manifold?
First of all, in this particular example, it's not quite a conformal manifold. It's really like a fat point. Right? I mean, it's all orders in lambda in perturbation theory, but not at any finite lambda because the actual, this lambda is supposed to identify it roughly with 1 over k of the k minimum model, and they're kind of discrete. So you can it's not quite a conformal manifold.
But the operator is marginal to all orders.
But here I want to emphasize that to all orders in perturbation theory and lambda does not mean that you have a actual one-parameter family, right? So you cannot turn any arbitrary finite value of lambda. So in other words, the claim here is that let's say here's lambda, and the theory that exists here corresponds to the AK minimal model, where k is roughly 1 over lambda. Okay, so you can get so lambda equals 0 is the accumulation point. So here I'm just saying there's this phenomenon where you can have the deformation that's marginal to all order, and it actually corresponds to accumulation point in the space of theories, but there isn't a line of fixed points.